Okay, so this class we are going to discuss about additions of angular momenta. The additions of angular momenta can be done in three different ways. The first one is for taking a multi-particle system, say example electron 1 and electron 2. Both the electron 1 having orbital angular momentum, say example L1 and L2 respectively. And if we are adding L1 and L2, then we will get it a total angular momentum, say example L, capital L. And this is the one way actually to add these two angular momentum of multi-particle system to get it the total angular momentum. And by adding a spin angular momentum of this electron 1 and electron 2 can also possible to get it total spin angular momentum as capital S. And this is one way by coupling two orbital angular momentum of the electrons, and otherwise adding a two spin angular momentum is the one way. And second way, by adding orbital angular momentum and spin angular momentum will give you a total angular momentum as J1 and J2, and by coupling these two further, J1 plus J2 will give you a total angular momentum of the particle J. If we are moving in this direction horizontally, L1 is the angular momentum for the particle 1 and L2 angular momentum for the particle 2, we will get a total angular momentum, and S1 is the spin angular momentum of the particle 1 and S2 is the spin angular momentum of the particle 2. By adding these two angular momentum, spin angular momentum, we will get the total spin angular momentum J. And by adding L1 and S1 of the particle 1, we will get J1, and similarly by adding the orbital angular momentum and spin angular momentum of the particle number 2 will give J2. And further, if we are actually adding J1 and J2, that means the total angular momentum J1 and J2 will give you J. So we can add in this direction horizontally also, and as well as we can add in vertical direction also. If we are adding in this direction, you see this is the additions of orbital angular momentum, this additions of spin orbital angular momentum, this additions of total orbital angular momentum. So we can go here. Additions of orbital angular momentum, and here this one is nothing but additions of spin angular momentum and this one additions of total orbital angular momentum. Angular momentum if we are adding, this is mainly for the multi-particle system. This all are actually for multi-particle system. Multi-particle system. And by adding, suppose L1 and S1, we will get J1. So this is nothing but LS coupling for a single particle system. Single particle system, and here again we can also do it the similar way, LS coupling for another single particle system. But if we are proceeding additions of angular momentum here with the additions of total orbital angular momentum and spin orbital angular momentum, we will get a capital J, and this one is again it is for multi-particle system, LS coupling for multi-particle system. LS coupling for multi-particles. So these are the way actually we can add two or more angular momenta. It may be either the purely orbital angular momenta or purely the spin angular momentum, or the mixture of orbital angular momentum and spin orbital angular momentum is also possible, and depends upon the condition we will get it either the system is in multi-particle or in the single particle system. Let us assume Hilbert space H1 is associated with the total orbital angular momenta, say example J1, H1 composed with H2 gives as H3, and here this is a Hilbert space H1 Hilbert space H1 and H2 subspace, we can write it Hilbert subspace, and H2 is Hilbert subspace 1 and this is a subspace 2, and J1 is capital J1 is total angular momenta of H1 Hilbert subspace 1, and J2 is the orbital angular momenta, total orbital angular momenta of Hilbert space Hilbert subspace 2, and by composing these two Hilbert subspace H1 and H2 we will get H3. So example, this is H3 system H3, and there is a H1 system and H2 system. If you compose these two Hilbert subspace and we will get H3, or we can say the H1 and H2 are the element of H3. So this is actually H1 is one subspace, H2 is a second subspace, and the composition of these two subspace is element of H3 system Hilbert space. So mathematically for writing for H1 system, H1 subspace, the angular momenta J1 can be written as state vector with the quantum number say J1 and M1. This is actually a state vector written in terms of quantum number. J1 is actually the total orbital angular momentum quantum number, and M1 is the spin orbital angular quantum number M1 or total magnetic quantum number. So this one is orbital angular quantum number, total angular momentum quantum number, and this M1 is spin angular quantum number or the magnetic quantum number. magnetic quantum number. Similarly, one can also write it for the Hilbert subspace 2 can be written as state vector with J2 and M2, and here again J2 is nothing but the total angular momentum quantum number of system H2, and M2 is again the magnetic quantum number of system to Hilbert space H2, and this one is element of J1 and M1 or the element of H1, and here this one is element of H2. More precisely we can write so this is H1 Hilbert subspace, and this subspace state vector can be written as J1 comma M1, and this is the element of H1 here, and Hilbertian subspace H2 can be also written with the state vector by representing a quantum number. State vector is in terms of quantum number J1 comma M1 ket and J2 comma M2 ket. If we are composing these two, we will get this third space, Hilbertian third space. Okay, let's see, by composing these two state vector, what would be the answer? That is our objective, to add the angular momentum. Okay, fine. So first let me start with finding the dimension of subspace and the dimension of composed space. Subspace H1 and H2. So for example, if J1 is actually 2, then for finding the dimension of subspace H1, so the dimension of subspace H1 can be determined 2J1 plus 1 is equal to, so here 2 multiplied by 2 plus 1, we will get 5. So that means the Hilbertian subspace H1 with dimension is 5. Then the value of M1, MJ1 or M1, we can write it. MJ1 will be minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5. This is nothing but a set, a complete set. And in other words, we can write it minus J1 2 plus J1. This value, MJ1 value, will actually move from minus J1 to plus J1. And similarly, for Hilbert space H2, we can write it J2, any example you can take it. So here I am taking as a 1 by 2, then the dimension of H2, this is for H1, and for H2, for H2, 2J2 plus 1 is equal to 2, 1 by 2 plus 1. Then it will give you 2. The dimension of subspace H2, dimension of subspace H2 is nothing but 2. It's a two-dimensional Hilbertian space. Then the value of mj, 2 moves from again minus j2 to plus j2 to plus j2. So the values will actually change from here minus 1 by 2, then 1 by 2. These two values only for mj2. Okay, let us look the composed space, dimension of the composed space. So the dimension of the composed space, H3 is equal to H1 composed. This is actually written in terms of tensor notation. It is called the tensor product. Then it is 2j1 plus 1 here H1, and this one can be written as 2j2 plus 1 is H3, the dimension of H3. Then we know that 2, if we are taking j1 as 3, we have taken j1, for example, j1 you take it as a 3 and j2 take it 1 by 2, then here 3 plus 1 plus 2 1 by 2 plus 1 . So we will get 6 plus 1 7 and 2 plus 1 3. So there are 21 there. Composed space, Hilbert space H3 with dimension of 21. Okay. By writing this combined state vector of Hilbert space H1 H2, we can write it a combined state vector. This is a J1 comma M1 is the state vector for Hilbert subspace H1, and J2 M2 is the Hilbert subspace H2. If we are writing with the combined state vector, then J1 J2 M1 M2. This is the terminology for writing the combined state vector of Hilbertian space subspace H1 and as well as H2. So the corresponding bra vector, this is written in Ket form. So for bra vector, we can write J1 M1 J2 M2 is nothing but J1 J2 M1 M2. Further, by using these two equations to write the completeness relation, for writing the completeness relation, for writing the completeness relation, so first sum over, another sum over. So it is outer product of this bra and Ket vector is nothing but the completeness equation. So for writing J1 J2 M1 M2, J1, J2, M1, M2. So sum over here the values of J1 and J2 is defined, then M1 and M2 will actually vary. So you can also write it this as MJ1, MJ2. So this value, the J1 will actually move from, M1 value will move from, so M1 will move from minus J1 to plus J1, and M2 also varied from minus J2 to plus J2, is nothing but completeness relation IN. Further, this equation can be written sum over J1 M1, I am writing this one with the tensor product, and J2 M2, and here this is a kit vector and bra vector, further can be written M1 is nothing but IN. Again the limits goes to minus J1 to J2, and M2 also minus J2 to plus J2. Again this same expression can be rewritten. M1 is minus J1 to J1 plus J1, and M2 goes to minus J2 plus J2, and here we can combine the system 1 with the outer product J1 M1, J1 M1, and system 2 J2 M2 and J2 M2 is nothing but IN. So the outer product is written by individual system and it composed with the tensor product further can be simplified into this term can be further written M1 is minus J12 plus J1 and M1 outer product J1 M1 and tensor notation composition and M2 equal to minus J2 2 plus J2 and J2 M2 and Z2 M2 is again it is another version of the completeness equation by composing a two Hilbert subspace H1 and H2. Fine. Now we know the combined state vector is represented with the ket vector J1, J2, M1, M2. This is the combined state vector of two Hilbertian subspace is written with J1, J2 and M1, M2 ket vector. Fine. Suppose if we are actually taking J1 is 1 by 2 and J2 is 1 by 2, then the value of M1 or MJ1 okay, is also having 2, one is plus of, another is minus of. and for mj2 or m2 is also provides 1 by 2 minus 1 by 2. There are two possibilities of the mj values. Then by using all these states, we can represent the state vector. Say example, j1 is 1 by 2 and j2 is 1 by 2 and m1 is 1 by 2 and m2 is also 1 by 2. This is one possibility for writing the state vector using above j1 and j2 values. And another possibility for writing the state vector 1 by 2 and 1 by 2 and here 1 by 2 and j2, so m2 may be minus 1 by 2. It's another state vector, possible state vector from this combination. And when you come to the third combination, 1 by 2, 1 by 2, minus 1 by 2, 1 by 2, third combination. For the fourth combination, we can write 1 by 2, 1 by 2, both m1 and m2 is minus 1 by 2. There are four state vector can be possible to write by using the j1 equal to 1 by 2 and j2 equal to 1 by 2 values. Again, if you look at the dimension of this particular j1 and j2, if you look at, if we write it 2j1 plus 1 and 2j2 plus 1 will give you 2 1 by 2 plus 1, 2 1 by 2 plus 1. Then this value will give you 2 by 2, there is a 4. This value will give you 2 plus 2. We will get totally the 4 state vector by composing j1 with j2. These 4 state vectors are a linear combination of the Hilbert space H3, or you can write it J3 system. So all these 4 vectors are the basis vector of J3. Or we can say these all are the orthogonal basis of H3. Okay. For writing the total angular momentum of H3 system with the operator form, for example, the J3 is the total angular momentum of H3. Total angular momentum of H3, and it acts as a state vector J1, J2. This is a combined state vector M1, M2 of H3 Hilbertian space. Okay, and this is the system again H3 and H1, H2. So the combined H1 and H2 is written J1, J2 and M1, M2. If we come, this is actually J1 is angular momentum, total angular momentum of J1 system, and J2 is angular momentum of H2 system, and J3 is angular momentum of H3 system. Now if we are composing H1 and H2, we will get H3. So the combined state of H1, H2 is written with the ket vector J1, J2, M1, M2. Now if this operator J3 total angular momentum acts on this combined state, what will be the effect? Fine. Let us start with J3 gives as J1 plus J2. If we are combining these two systems, H1 and H2, then we will get it a H3. So the additions of two angular momenta J1 and J2 will give you J3, and for this particular case the J3, if it acts on J1, J2 and M1, M2, can be written as, or otherwise take the state vector on both the side of this expression. So J1, J1, J2, M1, M2 plus J2, J1, J2, M1, M2. For H1 Hilbertian space subspace, what are the eigenvalues? So we have to write it, what are the eigenvalues? So J1 square, we can write it, J1 square is the total angular momentum, is called total angular momentum. All the possible operator I am listing out for H1 system. Then J1Z is nothing but the angular momentum along Z direction. Angular momentum along Z direction. This is for H1 subspace. And J1 plus minus or the raising and lowering operator operators. So these two are the Hermitian operators. This is nothing but non-Hermitian operator. Suppose if these all three operator acts on this state, yeah, combined state. So what are the eigenvalues? Okay, what are the eigenvalues? So example J1 square, if acts on J1, J2, M1, M2, then this system J1 is associated with Hilbert subspace H1. So this total angular momentum J1 square only play with this quantum number J1 in the state vector. So this will play with here only, and it gives J1 into J1 plus 1. So when this operator acts on this state vector will give you a eigenvalue. So that eigenvalue is nothing but J1 of J1 plus 1. So H cross square will also come. So H cross square, then state vector J1, J2, M1, M2 can be written. And when the angular momentum along Z direction acts on the combined state vector, then J1Z acts on J1, J2, M1, M2. This is actually the angular momentum along z direction. It acts on, this is for Hilbertian subspace 1, acts on the magnetic quantum number m1 to gives the eigenvalue m1 h cross, then j1, j2, m1, m2. When the raising operator and lowering operator acts on the combined state vector J1 plus minus acts on combined state vector so this raising and lowering operator play with the magnetic quantum number m1 because J1 and m1 is associated with the Hilbert subspace h1. In this case, we will get it J1 in J1 plus 1 minus m1 plus or minus 1 h cross. Then this is nothing but the eigenvalue when this operator acts on this state vector J1, J2, M1 plus minus 1, M2. Such a way we can also write for the Hilbertian subspace H2 and the total angular momentum J2 and its associated operators acts on the state vector, combined state vector. So example here J2 square is the total angular momentum of system H2 subspace acts on a combined state vector J1, J2, M1, M2. Again it gives another eigenvalue. That eigenvalue is nothing but J2 of J2 plus 1 my h cross square then J1, J2, M1, M2. If J2 is at the angular momentum along z direction for Hilbertian subspace H2 is written, and this operator acts on a state vector, it gives, this will actually play with the angular momentum quantum number J2, and this will J2 is it play with the angular spin magnetic quantum number M2, and it produce M2 H cross eigenvalue and J1, J2, M1, M2. Suppose the raising operator, non-Hermitian operator, acts on a combined state vector, we will get it the eigenvalue with J2 of J2 plus 1 minus M2 of M2 plus minus 1 with square root H cross, then Z1, Z2, M1, M2 plus minus 1. So far, if we look at the list of Hermitian operators, if we look list of Hermitian operator of both the system, J1 square, J2 square, Z1 is at, Z2 is at, these four are the Hermitian operator and suppose these operators commute with each other. So example, Z1 squared commute with J2 squared and Z1 squared commute with Z1Z and Z1 squared commute with J2Z and Z2 squared commute with Z1Z and Z1Z commute with Z2Z. It gives 0. The reason is that the Z1 and Z2, these two systems are two independent systems. So when it commute with each other, it will give 0. And as well as you look at Z1 square and Z1Z will give 0. And Z1 square and J2Z also 0. And in other words, we can also say the J1 squared and J2 squared all are actually a number, numerical values. For example, J1 squared is nothing but J1 and J1 plus 1 and Z2 squared is nothing but Z2 of Z2 plus 1. This is purely on number. If two numbers commute with each other, then it will give you a 0 value. Or the scalar, if two scalars are commute with each other, we will get it a 0 value. Then we could actually say these operators here, J1 square, J2 square, J1Z, J2Z, all are actually, we call it a complete set of commuting operator. Complete set of J1 square, J2 square, J1Z, J2Z, all are a complete set of commuting operator. Complete set of commuting operator. That means these all the operator sharing a common eigenvalue and sharing a common eigenvalue is J1, J2, M1, M2. It is eigenstate, common eigenstate or common eigenvector. This type of system, two independent system, when it coupled with each other, we call it this type of system or uncoupled system, or all these basis vectors whatever so far we discussed, we call it these are uncoupled basis. Two independent angular momenta, coupling of angular momenta, coupling of two independent angular momenta is nothing but a uncoupled system. And physically how it looks, the coupling of two independent angular momenta. So example, this is, we are taking in z direction in this axis, and suppose we have a system with the angular momenta J1, this is nothing but a J1, and there is also another system with angular momenta J2, angular momenta Z2. Both the system Z1 and Z2 precede in Z direction, and the vector addition of these two Z1 and Z2, if we look at the vector addition of J1 and J2, we have to make the parallelogram. So the parallel line to this one, okay, then it gives us this will come here. Again, the addition of J1 and J2 may also precede along Z direction. This is nothing but J1 plus J2. And the height of this one, if we take it, this one is nothing but m1 from here, this height, and this one is nothing but m2, and this value will give as, from here to here, it will give m1 plus m2. The J1 is precise in Z direction and J2 is also precise in G direction. These two systems are two independent systems or two independent angular momenta, and J1 is the Hilbert space belongs to H1 subspace and J2 is belongs to Hilbert subspace H2, and if we combine these two systems we will get it a J3, that J3 is nothing but J1 plus J2, and the Hilbert space is H3. We could actually say J1 and J2, J3 all are element of H3, and J1 is element of H1 and Z2 is element of H2 and Z3 is element of H3 only. So far what we discussed is the uncoupled basis or uncoupled system. When we move to the coupled system or the coupled basis, the Hilbert space H3 can be written, Hilbert space H3, the total angular momentum J3 square for H3 Hilbert space can be written as J1 plus J2 square, because the vector model for the coupled basis will be, again this is G direction, and if your system is precise like it is J1 if it precise and Z2 if it precise, it is nothing but Z2 and the vector sum of J1 and Z2 vector sum of J1 and J2, we have to make it the parallel line here, and to extend this line. So if you look at this is the parallelogram. So this line, this area provides the parallelogram. So these two lines are parallel with each other and these lines also parallel with each other. These two lines are parallel with each other, these two lines are parallel with each other. And this is a J1 system, this is a J2 system, and the resultant value of J1 and J2 will be J3 here. And this J3, according to the parallelogram law, if J3, if you want to find out, we have to take the square of sum of these two value, J1 square and J2 square. Sorry, the sum of J1, J2 and its square value will give you J3 square. If this is the case, and the difference between the coupled and uncoupled, this is nothing but a coupled basis or coupled system. J1 and J2 precise different from the z-axis, and the sum of J1 and J2, that is nothing but J3. J3 precise with z-axis. J1, J2 do not precise with the z-axis, but the vector sum of J1 and J2 will precise with z-axis. So this is nothing but precise. J3 is precise in z direction. In the earlier case, J1, J2 will also precise in z direction, and vector sum of J1 and J2 also precise with z direction, but here z1 and z2 precise with their own axis z1 z2, and the vector sum of z1 z2 precise with z direction. So this is nothing but the coupled system or coupled basis. Mathematically, for writing the coupled system of Hilbertian space H3, J3 square is nothing but the sum of square Z1 plus Z2. Further, this expression can be written as a plus b whole squared. So a plus b and a plus b, we can write it. So Z1 plus Z2 and Z1 plus Z2 can be written in this form, or this will actually gives as Z1 square plus Z2 square plus 2 Z1 and Z2. Suppose if we are writing the value of the Z1 in Cartesian system, we can write it Z1x with unit vector plus Z2x Z1x, Z1y with unit vector and Z1ez with unit vector ez. And similarly for writing Z2 angular momentum of system Z2, we can write it Z2x x unit vector, Z2y y unit vector, Z2ez ez unit vector. Then taking the product of these two, Z1 and Z2, here product of these two, so Z1x, Z1y y, Z1ez ez, Z2x x, Z2y y, Z2ez ez cap. Then multiplying these two, x dot x, it will be 1, then Z1x, Z2x, and x dot y, x dot ez will be 0, then plus Z1y, Z2y plus Z1ez, Z2ez. However, we know that how to write the operator Z1 x by combining the raising operator and as well as the lowering operator. So Z1 plus Z1 minus divided by 2 will give as Z1x. And similarly, Z1y can be written as Z1 plus, this is a raising operator and lowering operator. Combining raising and lowering operator, we will get Z1x. And Z1y also, by doing this way, the difference of these two raising and lowering operator will gives us Z1y. And for Z2x also we will get it Z2 plus plus Z2 minus divided by 2, and Z2y is nothing but Z2 plus minus Z2 minus divided by 2. Now if we are feeding all this value to this expression here, to find the product of z1x, z2x, we can write z1x is nothing but z1 plus z1 minus divided by 2 and z2 plus z2 minus divided by 2. Then we can take 1 by 4 outside. So z1 plus z2 plus z1 plus z2 minus z1 minus z2 plus z1 minus z2 minus. And again, to get the value of z1y with z2y, z2 plus z2 minus divided by 2, z2 plus z1y minus z2 plus minus z2 minus divided by 2. Then take 1 by 4 out, then z1 plus z2 plus minus z1 plus z2 minus, multiplying these two, and again minus z1 minus z2 plus, then plus because 2 minus is there, so z1 minus z2 minus. If we feed this value here in this expression, we will get it z1 z2 is nothing but 1 by 4 of z1 plus z2 plus z1 plus z2 minus z1 minus z2 plus z1 minus z2 minus, keep it 1 by 4 outside, then z1 y dot j2y is also there, then plus z1 plus z2 plus minus z1 plus z2 minus z1 minus z2 plus z1 minus z2 minus, then plus here 4 times z1 is at z2 is at. So if we multiply 1 by 4 inside, so this 4 gets cancelled, again we will get back this. Then if we look here, so z1 plus z2 plus z1 plus z2 minus, look it, this 2 term gets cancelled, and when we come here z1 minus z2 plus with positive sign, here z1 minus z2 plus is negative sign, again this will also go out. Then remaining term z1 z2 by keeping 1 by 4 out. So this is a 2 times J1 plus J2 plus J1 plus J2 plus. So twice J1 plus J2 plus, then again here also J1 minus J2 minus and J1 minus J2 minus, it is a twice, then plus 2 J1 minus J2 minus plus 4 J1 is it, J2 is it. So this will come so this will be all right. So here this will be minus sign plus this will be negative sign. If you look here, J1 plus J2 minus J1 plus J2 minus gets cancelled, and similarly when you come here J1 minus this 2 gets cancelled, then the remaining term we can write here 2 times J1 plus J2 minus plus 2 J1 minus J2 plus, then plus 4 J1 is it, J2 is it will be there. Now if we place the 1 by 4 inside, so we will get it 1 by 2 J1 plus J2 minus plus 1 by 2 J1 minus J2 plus, then J1 is it, J2 is it. It is nothing but J1 or J2. If we put this value, the product of J1 and the J2 here in this expression here, further J3 squared is nothing but J1 squared plus J2 squared plus, so twice 1 by 2 J1 plus J2 minus 1 by 2 J1 minus J2 plus J1 is it, J2 is it. Again we can simplify J1 squared plus J2 squared plus J1 plus J2 minus J1 minus J2 plus, it is alternative, plus 2 Z1Z, Z2Z. This is actually total angular momentum of the system H3. And if we look here to list out the Hermitian operator, so J3 square and Z1 square, Z2 square and Z1Z, Z2Z and then Z3Z will also come. So these all operators are Hermitian operator and with commute with each other. Let's see some example. I am taking J3 square commute with J1 square, commutation is equal to J3 square commute with Z2 square, J3 square commute with Z1Z and Z3 square commute with Z2Z, J3 square commute with Z3Z is nothing but Z1 square, Z2 square and Z1 square, Z1Z, Z1 square, Z2Z, Z1 square, Z3Z and Z1 square, Z3Z, then J2 square with J1Z, Z2 squared with J2Z, Z2 squared with J3Z, Z1Z with J2Z, Z1Z with J3Z and J2Z with J3Z. So etc. It all will gives us 0. The commutation of all these operator gives us 0. Let's check one example. Is it giving you 0 or not? We will take J1 squared with J3 squared, first commutation. First of all, these operators are nothing but a number. J1 squared is nothing but J1 of J1 plus 1 and J3 squared is nothing but J3 of J3 plus 1. All are as an eigen value of that operator. By using a commutator identity, we can write it. So J1 squared, but J3 squared, just now we calculated J3 squared value. J1 square, J2 square, J1 plus J2 minus J2 plus J1 minus J1Z, J2Z. By using a commutator identity, say example A comma B plus C, the answer is nothing but A commute with B plus or minus A commute with C. This is identity. Now if we take it here, j1 square commute with j1 square plus j1 square commute with j2 square. We can take it, no problem. Yes. Then plus j1 square commute with j1 plus j2 minus plus j1 square commute with j2 plus j1 minus plus j1 square commute with 2 j1z j2z. Then this is nothing but a self commutation. This one is 0, so we no need to worry about that one. And check it, j1 square and j2 square, have it becoming a j1 square to becoming a 0. Now take j1 square j2 square. As we already discussed, these two are two independent systems. So if two independent systems commuting with each other, it will be 0, though we have to verify how it is actually 0. j1 square j2 square minus j2 square j1 square. But the value of j1 squared is nothing but j1 of j1 plus 1 and j2 squared. These are all eigenvalue what I am writing here. j2 of j2 plus 1 and minus j2 of j2 plus 1 and j1 of j1 plus 1. Of course, if we put actually the j1 is 1 by 2, j2 is also 1 by 2, 1 by 2 of 3 by 2 and 1 by 2 of 3 by 2. So there is no difference if we are multiplying this term followed by this term or multiplying by this term followed by this term. The answer will be the same because j1 and j2 are purely on a number. So if we are multiplying two number, say 2 by 3 minus 3 by 2, we will get it 0. So this value is again it's 0. So this term also becoming 0. Now come to the third term, j1 square comma j1 plus j2 minus. Again, if you look at here, a comma b c commutation. So by keeping c, a commute with b, and by keeping b, a commute with c. This is the commutation identity. By using this identity, we can write here j1 square commute with j1 plus by keeping j2 minus and plus j2 minus by keeping j2 minus j1 square j1 plus by keeping j1 plus j1 squared commute with j2 minus. Look at here the commutation between a Hermitian and non-Hermitian operator. So the commutation of Hermitian and non-Hermitian operator always gives 0 only. So this will be 0 again, and when you come here again this will be also 0, because J1 is the Hermitian and J1 plus is a non-Hermitian. Here J1 squared is the Hermitian, J2 minus is a non-Hermitian operator. If it commute with each other, this will give again it is 0. So how it is actually giving 0, we will check it. So I am taking only this term J1 squared J1 plus. First verify this one. So this is nothing but J1 squared J1 plus minus J1 plus J1 squared. Then J1 squared is nothing but J1 of J1 plus 1. It is again purely a number and commute with the non-Hermitian operator, the multiplying with the non-Hermitian operator, minus J1 plus J1 of J1 plus 1. So there is, this may be the vector value and this is a number. If multiplying any number with vector is same as multiplying a vector with a number. So example 2a is equal to a2. This is actually a number, scalar quantity. This is a vector quantity. Suppose if we are taking, then if we are multiplying a scalar with vector is same as multiplying vector with the scalar. So in that case again this term will become 0. If this is 0, then this entire term will become 0. And similarly this term will also become 0. So the only term left is the last one, and let's see how it is becoming 0. So I am taking this last term J1 squared comma 2 J1Z. Hello.
Sir.
Yes sir.
I am Professor Bajpayee from GGV.
Yes sir, please tell me sir.
We have received the sanction letter also.
When you received sir?
I think today.
Today at what time sir?
Morning.
Oh morning.
When I was talking to you now, in the office I received this bill.
Okay, I am not actually received so far. Okay, I will check it again today sir. Okay.
But they have given very less amount.
How much sir they have given?
I think 92 or 94.
Oh, that is also good, but I don't know how much we have received it. I am not checked.
Your other department, how much they got?
Mathematics they received 27 lakh.
Okay.
Okay sir. Okay, thank you sir.
Okay.
Okay, thank you sir. Okay. Yes. What happened sir?
Actually, you are using that remote, so that is camera's remote.
Oh, this can be edited, na? Okay. Sorry. So J1 square commute with this system so by keeping you can take it to outside J1 squared J1 is z. You see again this will become 0, J2 is z plus J1 is z, J1 squared J2 is z. So this will become 0, again this will become 0, so the entire value will become 0. Then we could actually say the operators J3 squared, J1 squared, J2 squared and J3Z are complete set of commuting operator, because these all the operator share the common eigenstate J1, J2, M1, M2. So further can be also written that J3 square, if it acts on this state, combined state, then we can actually write it J3 of J3 plus 1 H cross square J1, J2, M1, M2, and J1 square J1, J2, M1, M2 is also J1 of J1 plus 1 H cross square J1, J2, M1, M2. Then when you come to write J2 squared acts on this state vector M1, M2, we will get it J2 of J2 plus 1 H cross square J1, J2, M1, M2. Then J1 is J3 is it. If it acts on this combined state vector M1, M2 will give as M3 H cross J1, J2, M1, M2. So if we want to write in this case, then the state vector here, the coupled basis, for coupled basis J1, J2, we will write it as J3, M3. Then these values, it is equivalent to this one. Then J1, J2, J3, M3. Instead of this, we can write this state vector. J1, J2, J3, M3, J1, J2, J3, M3, J1, J2, J3, M3. Okay, so in the next class, we will discuss the Lebesgue-Coulomb coefficient for determining the additions of angular momenta.